All right, so we'll step through. There are just a few steps in this pipeline, so this should be relatively quick. The first step here is this WCS creation step. What this is going to do is attach a JWCS object to the file and calculate the SIP approximation. And so this will then allow you to translate from detector coordinates to world coordinates in the outputs. So in this case, so I've got a link here to the full description and documentation of this step if you want more details. There are no optional arguments for this step to worry about, and it uses the distortion reference file from CRDS. So in this case, I am going to loop over the files, and I'm going to create an instance of, I'm going to actually read in each file into an image model. And then what I'll do is create an instance of this assign WCS step. I'll set the output directory and save results like with the pipeline above, and then use the run method, call the run method, and in fact, I'm calling it on the file name. So this line here is actually not necessary. So we'll loop over the three. This one, the three files, this is a relatively quick step. So the output of this step, what it's going to do is it's going to take the input file name and it's going to tack on this assign WCS step suffix when it creates the output files, which you can see here. So in this case, what I'll do is I will use the JWST data models to open one of these output files so that we can have a look at what's going on in there. First thing to do, let's look at the WCS, and we can get there using the metadata attribute of the data model. And so you can see this is kind of hard to interpret, but basically what it's showing is that the WCS is a series of offset functions and 2D polynomials all kind of stacked together, which then are going to allow you to translate from one coordinate system to another. And in fact, if we go here and we look at which coordinate frames are available, we have 4 different coordinate frames that we can translate between, rather than simply detector to world. So this just to show the input frames to this for the full translation. Input frames are in the detector coordinate system in units of pixels, and the output frame is in world coordinates in degrees, are in units of degrees. Alicia went over this in a little bit more detail in the first JWebbinar, but I'll just show briefly how to do a transform. So what we're going to do here is we're going to use the go into the meta WCS again. We're going to use the get transform function, and we'll create a function to transform from detector coordinates to world coordinates. And so we'll save that function. We'll also create a function to do the inverse. So now we're going to go from world to detector. So let's look. The next cell. What the next cell is going to do is just show a small cutout of one of the cal files. So this is just centered on these 3 sources. You can see we're only looking at a space that's 150 pixels on a side. So always remember to close your files when you're done. But so let's say you've got your 3 sources and you've got their XY positions here, and you want to know what are the corresponding RA index values for those sources. So all you need to do is call your detector to world transform function that we just created. You can provide it a list of X values and a list of Y values, or you can provide it just a single X value and single Y value. And you run Run the transform, and you can see here we have running RIndec values of those sources. And then the opposite case, say you have a target, you know the RIndec, and you want to know where that target is going to fall on the detector in your image. Use the inverse transform, provide the RIndec values, and here you can see we're providing just a single value instead of lists of values. That will calculate it for you, and it'll say your source is located at X, Y, of these numbers. After the WCS is added, the next step is the flat field application. So again, there's a link to the full description of the step. There's a single optional argument, but it only applies to near spec data, so we're not going to worry about that here. And it uses the flat field reference file from CRDS. So again, what I'm going to do, go over the files. For each one, I'll create an instance of the flat field step. I'll say I want to save the results, and then I'll run it using the file name. So in this case, we'll see that the output files are listed, the file names are flatfieldstep.fits. So let's just look, just to show the difference, basically. We'll load the data from one of the input files to this step, right, which was an output from the assigned WCS step. And we'll load the data from one of the files that was just saved here. And just to make the images a little bit more pretty, there are a few pixels in the images that were saturated in all the groups up the ramp that Carl was talking about. So in that case, the slope fitting gives them a value of 0. So in this case, all I'm doing is finding those pixels that have a slope of 0, and I'm setting them equal to 1. And that's really just to make the image that we're going to look at look a little bit nicer. Then just to show, we'll take the ratio of the science data before and after, and we should get back the flat field that was used. First, we'll look at the data output by the flat field step. So here it is. Again, megajanssens per steradian. These are some of these trouble pixels that we set equal to 1. You can still see a few of them. Then let's just look at the ratio before and after, which is basically the flat field. And there it is. So next is the flux calibration, or the photometric calibration step. This step is going to go into the photom reference file in CRDS. It's going to look up the translation coefficient to go. Well, that's interesting now. To go from yen per second to megajanssens per steradian. And the other thing it's going to do is go into this pixel area reference file, and it's going to attach that as a new extension in the output files. And so there are no optional arguments to worry about again in this step. And I should also point out there are a couple new header keywords that will be populated given the pixel area. So we'll look at that. And I'm going to loop over the files, create an instance of this photom step. Let's say that I want to save the results and run. In case the output files will be photomstep.fits files. So what I want to do here is I will use fits to open one of the output files so that we can look at the file format. So here you can see this is similar to what we saw when we ran the entire pipeline. But so this area extension is now new. This contains the pixel area map, a relative pixel area map across the detector. So the other thing I wanted to do is look at the header of the science extension. And so what I'm going to do here is, in this header, I'm going to look at the Pixar SR, and Pixar A2 keywords, which are new. These list the mean pixel area in steradians and also in square arc seconds. And these are values that were pulled from the Flux Cal reference file. Let's take a quick look at this new pixel area extension. We'll pull out the data associated with the area extension. And we'll also pull out the science data so that we can look at it. Let's look at this new pixel area map. See here, it's normalized to a value of 1 in the center of the detector. And then you can see how the relative pixel area changes given the distortion. And let's look at the science data associated with that. So here now we're in megajansons per steradian. Are these 0 slope pixels again. Yes, so this now is going to be the input to the level 3 pipeline. But we will move on here to the resample step so that we can create these I2D files. So again, a link to the description. There are a bunch of AstroDrizzle style input parameters that you can play with. And let's actually, just to remind you, we'll use the spec attribute again to list those here with their defaults. Let's now, again, loop through our 3 files. We'll create an instance of the resample step, save the results, and run. Okay, since we're running step by itself rather than the pipeline, the outputs are going to be called resample step.fits. Right? Whereas when we ran the pipeline, the full pipeline, the outputs were I2D.fits. See here, though, as it's drizzling each file, as it's resampling each one, we're now going from the nominal 2048 by 2048 array to a new array size that is not necessarily square. At the bottom here. Oops. Let's just read in the data from these 3 different files. And we can show all 3. They all look more or less the same because our dithers are quite small in these. And so now again, we're showing the array is not quite square because we've resampled to remove distortion. We'll go back. So this is the equivalent of looking at the cal file here. You can see this is without the resampling step being run. So now we're back to this 2048 by 2048 file. So this is what will go into the CalWeb Image 3.